live.
Hello, everyone. Thank you for joining us today for our live session, our live question and answer session. We are going to take questions both from email and from the audience who is on with us live. So, Chris, why don't you go ahead and say hello?
Yeah, welcome everyone. We're of course now running 2 MOOCs through Coursera and 1 through Udemy. So hopefully it's a lot of people online, a lot of questions to ask and answer. I'm coming to you again from London, where I'll be for the next couple of months, and ready to take your questions.
Excellent. So the first question is from David Cook, who sent a question in via email about the recent EHT black hole image from the galaxy M87. And the question is, why is the black hole actually visible? Wouldn't it be obscured by the ring of fire if the event horizon was a sphere and not a disk?
That's a good question. The ring of fire, or the firewall, as it's often called, is a purely theoretical construct. There's no physical mechanism for creating the firewall, so it's very hypothetical. And in fact, in the simplest form of black hole theory, there is no firewall. So all there is an event horizon, which is black. Yes, the black hole should be spherical. The event horizon should be close to a sphere. But what you're seeing is, of course, the backlighting or the silhouette of the black hole against an accretion disk. So the accretion disk is a disk. So you have a spherical geometry of the black hole and then a disk geometry. And what happens is the part of the disk that's coming towards us is Doppler boosted to be brighter, and the part of the disk that's moving away from us is Doppler boosted to be dimmer. And that's why, in the way the image is presented, one half of the disk is glowing more brightly than the other half. And there's some distortions that are part of general relativity. So that's the basic explanation for why it looks the way it does.
All right, the next question is from Vidhi Gajra, who's on with us live, who asks, why do objects fall in a spiral manner in a black hole and not in a straight line?
Yeah, good question. I mean, the simplest answer is that space is big and the black hole has a significant amount of gravity, but for objects moving through space that fall into the gravitational pull of a black hole, they're very unlikely to have a plunging trajectory, which is to say their initial vector is very unlikely to have pointed directly at the event horizon. And so it's most likely that they have a glancing trajectory, or they're coming at some angle, and the black hole's gravity just causes them to gradually deviate. And so the most likely scenario is, in fact, a spiraling in. Ready for the next question.
All right, thank you, Chris. The next question is from Wolfen Bree, who's on with us live, who asks, do you believe the universe will eventually fizzle out and die, or do you believe it will be reborn?
Well, the current scenario, based on the best observations we have, is of endless expansion. So an open universe where the expansion will accelerate due to the presence of dark energy. If not for dark energy, there would be deceleration, but even without dark energy, the dark matter would be insufficient to overcome the expansion and cause a recollapse. So pretty much under any scenario, given what we know about dark matter and dark energy, the universe will expand forever. And that means a rebirth is extremely unlikely. What in fact will happen is that physical processes will continue and the universe will gradually sort of degrade in the growth of entropy, a natural result of the law of thermodynamics, with stars dying out and bound gravitational systems like solar systems and galaxies evaporating so that things get spread more thinly into space, microwave background stretching out due to the expanding universe to become even lower energy than it is now at about 2.7 degrees Kelvin, and then eventually even black holes evaporating. So the final state of the universe is one of complete disorder, including the decay of normal matter if current theories of physics are correct. Ready for the next question.
All right, the next question is from Steve Koski, who is on with us live, who asks, have you heard of the Lehrer Project, the ones who have a strategy to intercept the object known as Oumuamua? And do you have any thoughts on their project or their efforts?
I've not read much about it, but I understand this is, a very ambitious attempt to intercept this object that is in a, this is extremely elongated small solar system body. It's very unusual. And it was so unusual it led to speculations that it might be an alien artifact. That's not true, however. Nature does know how to make extremely elongated asteroids or small solar system bodies. Intercepting it, again, the question will be for what purpose, is extremely difficult because it's first of all, it's not really due to come very close to the Earth, and second of all, its velocity is such that so capturing it is really not a plausible scenario to get it into, say, an Earth orbit. I don't know any way with current technologies that can be done. So the whole project of intercepting it seems basically a little far-fetched to me. Ready for next question.
All right, the next question is from Guido Baccaglini, who sent a question in via email. And the question is about electron and neutron degenerative pressures. And can you explain how that works in neutron stars and what the relationship is between the Pauli exclusion principle and the Planck length in terms of separation of particles?
So, as a standard force of physics, pressure, results from various states of matter. So gas has a pressure that's defined by the perfect gas law. That was relationship described by Robert Boyle 250 years ago. More exotic states of matter also have pressures, and those pressures are due to inter-atomic forces. It could be due to an electrical force, or neutral material, it's due to the collision energy or the motions of the particles. So the pressure increases with temperature in a classical physics sense. The pressures that exist within white dwarfs and neutron stars have a somewhat different basis because they're not kinetic type pressures. In other words, they're not related to the temperature of the material. They're quantum pressures that are associated with a strong principle in quantum theory where no two particles can have exactly the same set of quantum properties, where that includes their spin, their charge, their energy, all of their various quantum properties, momentum, and so on. And in physics, what that corresponds to is a pressure. It's the inability of two particles to occupy what we would call in physics a phase space associated with all their properties. And so you can calculate that pressure, and for a white dwarf, this pressure comes from electrons and their quantum properties. And so that degeneracy pressure is what stops a white dwarf from collapsing to an even denser state and keeps the core of a dead star at a particular size. The sun will, in fact, have this end fate once fusion is over. If the core of the dead star is massive enough, then the gravitational force can overcome even this electron degeneracy pressure. And so it forces electrons and protons to merge in a reverse version of beta decay. And then the neutral particles that result, neutrons, have no electrical force. And so there's no electrical pressure operating within that material. And they essentially sit as close as possible to each other, almost like eggs in a carton, if you imagine that. And the only force that stops them merging completely together is an analog of electron degeneracy pressure for neutrons due to their quantum properties. And so neutron stars are kept at a particular size, much denser state of matter than white dwarfs, tens of thousands or hundreds of thousands of times denser by neutron degeneracy pressure. And the typical scale length here is an internuclear scale length, a typical distance between nucleons in atomic nuclei. Ready for the next question.
Our next question is from email as well from Peter Bafus, who asks, when discussing the possibility of life on exoplanets, an assumption is being made that liquid water exists on those planets within the so-called habitable zone. Where did Earth's water come from? And if it was something like a comet, can we calculate the probability of comets impacting other planets to figure out if there's actually water on these other worlds in the habitable zones?
Yes, so it's correct that the question of habitability of exoplanets does make an assumption, quite a strong assumption, that liquid water will be available. And of course, we know that liquid water can exist in various settings. It doesn't have to just be in a liquid body of water protected by an atmosphere on an Earth-like planet, as in our case. The water could exist by being underground. It could be in a cold place, an outer solar system place, where that water is liquid because of pressure from the rocks on top. Mars probably has subsurface aquifers that are liquid for this reason, because generally surface of Mars is below the freezing point of water. So there are definitely different situations where liquid water can exist that are not quite the same as the Earth-like situation. And so this habitability is a flexible concept. The question of where the Earth got its water, and therefore also where other Earth-like planets might have got their water, is actually still an open question. The theory for the last few decades, the predominant theory, has been called the late veneer theory, where after the Earth formed, there were oceans were mostly consisted of steam, so there was some water as part of the Earth's formation, but the basic bulk of the Earth's oceans was presumed to have been deposited by icy and rocky material in the inner solar system that hit the Earth in the first 50 to 100 million years. And so indeed deposited by comets or other icy material from the outer solar system. That theory has come into question because we've measured the isotopic abundance of water in several comets now. It's, I think, at 3, maybe 4, by which we're talking about the ratio of normal water to deuterated water, or sort of heavy hydrogen, water with heavy hydrogen in it, an extra neutron, so an isotope of water. And those ratios in comets, well, in one case they do match the Earth's oceans, but in a couple of other cases they don't match the Earth's oceans. And so this theory, having been tested by measuring the isotopic ratio of water in a couple of comets, is in question a little bit. We obviously need more comet samples to be sure. An alternate theory that was propagated particularly by Mike Drake, who died a few years ago, worked at the University of Arizona and was head of the Linear Planetary Lab, was that the water in the Earth's oceans actually came from the deep core of the Earth. So the Earth's water was actually there at the birth of the Earth, and it eventually came up, bubbled up through the rock by processes when the Earth was still hot and young. So the question of the deep Earth inventory of water, the water-Earth inventory in deep rock, kept there under pressure and extreme heat, is very difficult to resolve because we simply don't have direct measurements of that part of the interior of the Earth. So there's a basic idea of where the Earth's water came from, and by extension, the water on other Earth-like planets, but there's still some significant questions about where it really did come from. Ready for the next question?
All right, the next question is from Siddharth, who is on with us live, who asks, what is the halo in the black hole image made of? Does some cosmic matter spurt out of a black hole when a star is being pulled in?
The halo in the black hole image, the bright part, remember these are radio waves, so it's just turned into color based on radio intensity, because these are not visible light waves. This is from the accretion zone around the black hole. So there's a zone where mass that is eventually going to fall into the black hole aggregates into an accretion disk. It turns into a disk because the black hole has angular momentum, it's spinning, and so there's a preference for material to spiral in along an equatorial zone and not along the poles. In fact, it can be ejected. Plasma can be ejected along the poles, leading to radio jets, which M87 has a radio jet and an optical jet. So this material that you're seeing in silhouette, the backlighting and the bright material, is an accretion disk, and it sits at a distance of 5 to 10 times the Schwarzschild radius of the massive black hole. Remember, the Schwarzschild radius in this case is about 10 times the size of the solar system. So these are the innermost zones of accretion around the black hole, where the material is actually generally quite hot. It does still emit waves of longer wavelengths, radio waves, millimeter waves, but much of the material is hot, tens of thousands or hundreds of thousands of Kelvin. And that's really what we're seeing in this image. Ready for the next question?
All right, our next question is from Eric Nicholson, who is on with us live, who asks, at what stage in the formation of the universe did black holes form?
That's a good question and still a very active research topic. It's not clear when the first black holes formed. So there are two parts to this question or issue. One is the possibility that black holes formed very, very early in the universe, in the first fractions of a second. These are called primordial black holes. So obviously the Big Bang was extremely hot, extremely dense, and the density when the universe was extremely small was sufficient that small regions of it could have been black holes. So black holes could have formed across the entire universe when it was tiny, just after the Big Bang. And these are called primordial black holes. And they could form at a very wide range of mass scales, ranging from essentially atom mass up to grams or maybe planet mass objects. Now, Hawking's theory predicts that black holes will evaporate, and most of these very small black holes, especially the ones that are subatomic, or maybe the grains of sand, a gram or a picogram or a microgram, these black holes will evaporate very quickly. And so they should not persist in the current universe. So primordial black holes really can only persist for 14 billion years in a particular mass range. And we're still looking for that particular mass range. The second form of black holes are just the normal stars, the first generation of massive stars that die and leave behind black holes. And there's speculation that those black holes that formed were actually quite massive. They were maybe 100 to 200 times the mass of the sun, so much more massive than the black holes we see formed by dead stars around us now. And those could indeed be the seeds of galaxies forming. So the question of whether galaxies form first or they're central black holes is also still an open question, one that we hope the James Webb Space Telescope will be able to resolve. So the issues of black holes in the early universe, either the tiny black holes in the very, very early universe, which currently we really don't think exist, or the big black holes that formed much more big than massive stars we see around us now, that could have been the seeds for galaxy formation, that issue could be resolved by the James Webb Space Telescope. So it's very exciting research. Ready for the next question.
Thank you. The next question is from Bob's Geo Jaws, who's on with us live, who asks, will 0 degrees Kelvin create a black hole? So when something reaches 0 degrees Kelvin, is that what creates a black hole?
It's not formally a question of temperature. There is nothing actually in the universe that is absolutely cold, because the universe is permeated by radiation left over from the Big Bang in the microwave background. That's at a temperature of 2.7 Kelvin. So there are very particular instances where you can have colder temperatures than that, but the generic temperature of the universe is essentially 3 Kelvin, and so you don't get 0 Kelvin anywhere. Black holes don't have a particular temperature. If they do, it's the Hawking radiation temperature, and that temperature is indeed very close to 0, because that's a very feeble amount of radiation, perhaps a billionth of a Kelvin. So that is pretty close to 0 temperature. So that's the sense in which black holes are close to 0 Kelvin in terms of their radiation. But black holes, of course, are formed in a situation of gravitational collapse where there's a lot of energy. So there's often very high temperatures in the situations that lead to a black hole. Ready for the next question.
All right, the next question is from Daniel Charmy, who sent an email asking, is the moon really in a perfect tidal lock, or are there some complexities and irregularities in its orbit? And if so, are those of any interest or importance?
The moon is indeed, as we see, tidally locked. It's obvious because we every month see the same face of the moon, so that the moon is in a synchronous orbit where it's locked to the Earth, and that's caused by its proximity and the fact that it's a fairly high-mass satellite compared to the planet. There are, however, of course, subtleties in its orbit of the Earth, and of course there's a very slow migration of the moon away from the Earth. So the tidal coupling between the moon and the Earth is actually slowly getting weaker, in the sense that due to transfer of energy angular momentum between the Earth and the moon is slowly getting further away from the Earth, I think by something like a centimeter per year. So if you play this forward like a billion or a couple of billion years, the moon will eventually get far enough away from the Earth that it will no longer be tidally locked, and it will start spinning on its axis the way other moons of planets do when they're further away. So yes, there are subtleties of the orbit of the moon around the Earth that are going to lead to long-term changes in this situation and the end of the tidal locking. Ready for the next question?
All right, the next question is from a live viewer, Dehi Buch, who asks, can you briefly explain the difference between an event horizon and a particle horizon?
Yes, there are different horizons in physics and astrophysics. An event horizon is a particular construct for a black hole. It refers to the imaginary, nearly spherical surface of a collapsed object where the escape velocity equals the speed of light. In other words, the event horizon there defines the region of space that's hidden from our view forever. So whatever went into the black hole to form it is lost from view. Nothing can escape from inside the black hole. Particle horizon is a little bit different. A particle horizon is usually referencing a situation in cosmology and an expanding universe where there's a distance beyond which we can't see because there's no way for any particle or light, the fastest moving particle of all, a photon, to reach us in the history of the universe. And so regions of space can exist within our model, say of the Big Bang and the expanding universe, that are hidden from view or that are unavailable to view because they were expanding away from us so fast, faster than the speed of light, that region remains beyond view. If the universe were eventually to decelerate enough, those regions might come within view. So the particle horizon in cosmology references the edge of our viewing. It's not a black hole type situation, though. It's a situation of expanding universe where there's just a limit in space and time to regions we can see. Ready for the next question?
The next question is from Marcos, who is on with us live, who asks, when do you think we'll have the technology to colonize the moon and or Mars? And what form of propulsion do you expect that we will use?
It's a good bet that we actually have the technology to colonize the moon and Mars right now. The ability to live on the moon and Mars and get there and come back safely, that's existed, for actually a few decades, and certainly it exists now. What's missing, of course, is a huge amount of money and investment in infrastructure to support even the minimal moon or Mars colony. You could imagine that in 10 or 15 years, there could be a very minimal moon colony and maybe 20 or 30 years a minimal Mars colony, by which I mean maybe 4 to 8 humans living on the surface, not forever in a fully self-contained way, but being resupplied by Earth or swapping out with other people. So that's a time scale that it could happen on. And as far as the propulsion required to get there, it's just conventional rockets. With the best rockets we have now, we know we can get to the moon in a few days, something approaching a week, and we can get to Mars on an efficient energy orbit when Mars is at closest approach in about 6 to 8 months. And it's going to be really hard to do much better than that. So once again, those technologies already exist. It's really a matter of the will and the enormous investment required to do it. Transformative propulsion technologies that would reduce those times substantially, especially the one to Mars, are really not on the horizon in the next few decades. Ready for the next question?
Excuse me. The next question is from is from one of our live viewers, and the question is, how do we calculate the size of the observable universe?
The observable universe size comes from the Big Bang model. So we take our measurement of the current expansion rate, the Hubble constant. We take our measurement of the matter and energy content of the universe, that is the amount of normal matter, and dark energy, and we run a model of what the expansion rate of the universe, or what the expansion history of the universe has been since the Big Bang 13.8 billion years ago. And if you do that, it's easy to calculate the distance to a particle horizon, that is the distance, the furthest distance we can see the distance beyond which no information could have reached us in 13.8 billion years. And formally, that distance, somewhat surprisingly, is about 3 times the look-back time in billions of years. It's something like 39 billion light years in any direction. And it is 3 times the age of the universe in years because the universe was expanding faster than light for the first roughly third of its expansion history. So that's the size of the observable universe. It succumbs from the model, though. So if our Big Bang model is incorrect, or our measurement of these parameters of dark energy, dark matter, and the current expansion rate are wrong, then that throws everything into doubt. But these are pretty reliable numbers now that are measured to an accuracy of 10%. Ready for the next question?
So we have a related question from Gitanjali, who sent an email, who asks, people say that the universe is expanding, which means it must have an external boundary. Is this boundary physically tangible or visible to the eye, and what lies beyond the boundary?
It's an interesting question. And formally, the universe does not have to have a physical boundary. It's not part of the model. It's not required, and therefore there's no reason to hypothesize it. We have an observable edge to the universe that we're talking about in the last question. And beyond that, there's just likely to be additional regions of space-time, probably filled with the same material, stars and galaxies, dark matter and dark energy that the universe we see has. And it could be much bigger than the observable universe. How much bigger is actually not specified by the model. That would require us to know more about the initial conditions for the Big Bang itself. So the physical universe can be much, much larger than the observable universe. And it does not have to have a boundary. There's no sense of any limit or edge to space-time as far as we know. That's a matter for conjecture, but as far as observation is concerned, we have not seen any limit. Ready for the next question.
All right, the next question is from one of our live viewers who asks, when do you think we will have the technology to discover Earth and Mars-size exoplanets?
We already are discovering Earth and Mars-sized exoplanets. In fact, the exoplanet boundary in a few instances has been pushed almost down to moon-sized objects. Microlensing, for example, which is a kind of specialized technique for detecting exoplanets and has not found a very large number. It does, however, have enormous sensitivity to low masses. And so microlensing has already found Mars mass exoplanets and is capable of finding even smaller objects. The limits of the Doppler method pretty much are around Earth mass or slightly smaller. It's just really hard to do spectroscopy accurately enough to find something much smaller than the Earth. The transit method, however, that used by Kepler is easily able to find smaller than Earth mass planets, Earth-sized planets. And it formally was finding planets about half the size of the Earth at the limits of its capability. So we've already found things smaller than the Earth, and we hope to continue to find smaller things than the Earth. Ready for the next question.
Okay, the next question comes from Siddharth, who asks, why did the people using the EHT look at a very distant black hole and not the one in the center of our own galaxy?
They've been looking at the one in the center of our own galaxy, and that is very likely to be their next spectacular press release. Not clear when, probably in a couple of months. They're going to leave a little gap for optimal press attention. So they have one in the can of our own galaxy. The reason they chose the big one is because it's more spectacular. This is a galaxy that's 55 million light years away. It's a black hole that's 6.5 billion solar masses. So it's a very spectacular splash to make with your very first black hole image, to pick such a huge black hole, almost the biggest black hole you could possibly find, that just sort of happens to be fairly close to us. 55 million light years is the relatively nearby universe. So this is by far the biggest black hole that close. So it makes a compelling target. The galactic center is, of course, much closer. It's only 26,000 light years away. But the black hole is proportionally smaller. It's 1,000 times smaller. And so it's actually not that much easier to make an image of the black hole in the galactic center than it is the black hole they've already published a few weeks ago. But we can anticipate that as being the second one. After that, it gets harder. There's a handful of other possible black holes they could image with current technology, but they're actually not going to be quite as spectacular as these first two. Ready for the next question?
So Kat K sent an email with kind of a philosophical question, and it's got sort of two related parts. And the first one is, how do scientists, astronomers, astrophysicists, and astrobiologists maintain and cultivate their motivation to conduct and pursue fundamental research when many of those questions will likely not be answered in their lifetime? And then how do they decide on scientific standards for measurements that can ensure that can be that their data that they're collecting now can be used in the future when techniques and things are different?
Yeah, these are good, deep questions about science. The question about what questions to try and address through science, through astronomy, is an interesting one, because our view of the universe changes over time. Our view of the universe is very different from a few hundred years ago, or even from 100 years ago, before we even knew there were galaxies, pre-1929. So the questions that are asked of nature through science do indeed change. But there's continuity, because the laws of physics don't change. So while we have newer laws of physics in the last century through the quantum theory, the foundation of Newtonian mechanics, the foundation of thermodynamics, these go back a couple of centuries, and they really haven't changed. There's still context for understanding the universe. And so there are contexts for asking questions in the future. When we do get superior theories, such as the quantum theory of gravity, we'll probably be able to ask different type of questions, because they'll be framed by a different theory of how gravity works and the microscopic world works. So there's continuity, and occasionally there is profound change in how we ask questions when a new theory comes along. But really, these evolutions and changes are quite slow. I mean, there's one major physics revolution every 50 or 100 years, so it's not happening from week to week or year to year or decade to decade. So within a single scientific career, these things don't usually change. And then there's equally continuity in the tools that astronomers use. So if people are worried about taking data now and then what will happen in 10 years or 100 years or 50 years, there's some practical considerations where people are worried. For instance, how is data stored? Now we have storage mechanisms that didn't exist 30, 40 years ago. Now we store data in the cloud. Our nature of computation has changed. And so we might worry what happens to these methods and these tools and our knowledge and our data going into the future. So far, we've been able to archive or preserve and pass down to future technologies the data and information we've previously acquired. And since so much more data is being acquired now than previously, all that was acquired, before the era of computers is essentially a drop in the bucket of knowledge. So storing the data and preserving it for future generations doesn't seem to be an issue. There's a concern about the hardware, because storage mechanisms physically are degrading, like CDs and DVDs. Those are not long-term persistent. But that doesn't mean the information is lost. The techniques of computing haven't also changed much. So the basis, the mathematical and computational basis of how people address data has been around since Claude Shannon in the 1950s. So once again, these are kind of long-term stable methods by which we manipulate data and store data and talk about data. So once again, they can be passed on from one generation of scientists to the next. But it was an interesting question. Thanks. Ready for the next one?
All right, the next question is from Salim Majid, and there are several other people who have similar kinds of questions, and it's, what would we see if we cross a black hole event horizon? Could we see a naked singularity, and just generally what happens when things move across the event horizon?
We'd love to know. We don't know, so we rely on theory, and we rely on theory knowing that our theory of black holes is incomplete, because the gravity theory does not accommodate quantum effects. And we know from work of Hawking and unresolved questions that he left behind and others are working on, that our lack of a quantum theory of gravity actually limits our understanding of what's inside a black hole. So the most conservative answer to the question is we simply don't know. The slightly more practical answer to the question is our best idea is that if someone were able to cross the event horizon of a black hole, a big one, they would be killed. If it was a small one, or a dead star type black hole would rip someone apart, but a huge black hole, like the one in the galactic center, you could survive passing in. You would survive passage, not be ripped apart if you were protected. There's a vacuum, of course. You would actually see what was inside. It's not clear that there's radiation in there. I mean, within the black hole, there's matter, and radiation can travel within the black hole. It's trapped within the black hole, traveling in circles, if you like. So it would be a bizarre situation, and nobody really knows what it would look like. The cusp or the singularity is not going to have any particular appearance because it's a gravitational cusp. It's not a cusp of radiation, and it's not generating radiation. And no light can really escape from an infinite density situation to travel outward. So it's unlikely that you'd ever see anything to do with the singularity. You'd probe it by experiments, presumably by if you brought in projectiles or particles that you could monitor and send them towards the singularity and watch what happened to them. That would be the best way of probing the singularity. So in some hypothetical situation, you could do experiments having succeeded in passing through the event horizon to understand the physical nature of the singularity and the regions within. But I don't think they'd look a particular way. I don't think they'd have a particular way of looking. Ready for the next question?
The next question is from a live viewer who asks, in LIGO, when we encounter a gravitational wave, both the interferometer reflectors as well as the laser light simultaneously expand and contract. So how can we see, or how can the change in fringes be detected?
What's being detected in LIGO is the difference in the way space-time behaves in two orthogonal directions. So LIGO, the two LIGO instruments, and now the one in Europe, the Virgo instrument, consist of evacuated cylinders with laser beams bouncing in a vacuum with mirrors at either end, combined at the apex of an L, if you like, that are separated by 90 degrees. When a gravitational wave passes through matter, through space or through the Earth or through any object, including the LIGO instrument, it flexes space-time in all dimensions, in 3 dimensions actually. It's a tensor wave mathematically, so it flexes in every dimension. And it will flex differently in 2 orthogonal directions because it's a wave, it has phase, and so it will flex one way at one time while it's flexing in an orthogonal direction at another time. And so the interferometer is basically looking at the difference in the flexing in these 2 directions or dimensions, and is doing a very clever differencing experiment. And that differencing experiment is, of course, looking for a tiny amplitude wave, a space-time distortion that's smaller than a proton, and that's, of course, what made LIGO such an amazing instrument. But that's what it depends on. So LIGO really wouldn't work and couldn't measure anything unless it had this method of comparing 2 orthogonal directions with 2 arms. Ready for the next question.
The next question comes from Robert Baker, who sent a question via email, and he asks, what type of telescope would allow you to detect signals from the Big Bang, or or closer to it than we have now?
Well, LIGO, we've just been talking about gravitational waves, and the theories of the early universe suggest that the very early universe, first tiny fraction of a second, were a time of intense gravitational radiation. It's not really with the same character as the LIGO signals from spiraling black holes. That's a very characteristic chirp signal, sort of crescendo gravity waves as the black holes spiral together. Black holes from the Big Bang are more likely to be stochastic or have the character of noise, a very particular kind of noise, so some random quality to them. But the Big Bang theory does predict that such gravity waves should exist. It also predicts that inflation, if inflation happens, should generate a very particular form of gravitational waves. So there are hopes to be able to detect gravitational waves from the universe itself, the entire universe, as a diagnosis of early universe physics, like inflation. There's no way that the current instruments like LIGO and Virgo are going to be able to detect these signals. They're small. They're actually very hard to predict their waveform, and they're likely to be much smaller in amplitude than the signals LIGO is detecting so far. But those signals almost certainly exist. They're to be detected by some clever new technique. So astronomers are thinking hard about how to do that. And it's possible that it might happen from space, where the noise levels and the noise levels go down, sensitivities go up, and you can do a much more powerful experiment. Ready for the next question?
The next question comes from a viewer who is on with us live, who asks, do you know of any projects in astronomy that amateurs can help in, just like planet hunters in TESS, helping to find new planets and analyzing light curves?
Definitely. I mean, amateur astronomers have impressive equipment these days. Many of them are using CCDs at the back end of their telescopes. They have telescopes of 5, 10, 20 inches that are tracking the sky and able to take long integrations. So certainly exoplanets, transiting exoplanets is an area where amateurs can do good work because it requires persistence, long time observations, but the targets are relatively bright, so what's needed, there's plenty of photons, and what's needed is precision. And so modest-sized telescope in a CCD can do that. Supernovae is another area because we expect one supernova to go off in a big galaxy like the Milky Way every 50 to 100 years. So if you were able to observe, 50 to 100 or a few hundred nearby galaxies, you might expect to see a supernova in one of them in a year of observing. And so networks of amateur astronomers they're already doing this kind of experiment, hoping to get lucky enough to see nearby supernovae. And those are very valuable to astronomers because they allow us to test the physics of a supernova explosion, since we're now applying that physics to the distant universe to measure the expansion rate of the universe. So it's very important work. Amateur astronomers also can play a role in hunting for small solar system objects. The hunt for planet X or dwarf planets tend to be very faint objects, but again, at that range of 10 to 15 to 20-inch telescopes, looking for moving targets, slowly moving targets. Again, a lot of patience required, observations over months and maybe years. Amateur astronomers can play a role there. And then there's a set of variable stars in the universe where the physics of the variability, maybe 50 or 60 different types of variable stars, each with distinct physical mechanisms, are not fully understood. And monitoring of variable stars by amateur astronomers can make a real research impact. So these are all legitimate areas of research that can lead, for example, to refereed publications just as professional astronomers do. And astronomers, amateur and professional, do collaborate on such papers all the time. So these are a set of areas, and there may be more I haven't discussed. Ready for the next question?
Okay, the next question is from a live viewer who asks, will black holes gain mass?
Yes, black holes are consuming material. They have gravitational pull. They draw mass in, and they do it fairly slowly. And because even if there's available mass, say for a big black hole in the center of a galaxy, the rate at which they can ingest that material is quite low. So for example, a massive black hole in the center of a galaxy, like the M87 black hole, if there are 6-7 billion solar mass black hole in a very massive galaxy, might be ingesting matter at the rate of, at a maximum, something like 5 or 10 times the mass of the sun a year, 5 or 10 stars per year. Now, the black hole won't typically be devouring 5 or 10 stars whole. It'll be devouring that amount of mass in a much slower way by the gas that stars lose when they age, that spirals its way into the center of a galaxy. So that's actually a very small rate of growth. A black hole that's several billion times the mass of the sun, only gaining 5 or 10 times the mass of the sun in a year, is, if you do the math, it's going to take a billion years or so, or a few billion years, to double in size or grow significantly in size. So black holes, essentially grow over cosmic timescales and not very rapidly. Ready for the next question?
Okay, the next question is from an email from Varnika Chowdhury, who asks, while Big Bang Theory talks about the creation of our universe, there is also talk about the concept of a multiverse. Is that possible, and how?
A multiverse is a purely theoretical concept, has no observations to support it. It emerges out of the idea of inflation, where the universe began as a quantum fluctuation in the vacuum, and then energy from the vacuum, a quantum effect, grew the universe, grew the space-time of the universe in the inflationary era. So the hypothesis, therefore, is that if the universe essentially was a quantum event, why were there not possible other quantum events in whatever the pre-existing situation in space-time was at the time of the Big Bang? So you can see that's a hypothesis, it's a speculation. To verify it, we'd have to have indication of these other universes, these other hypothetical space-times out there beyond our own space-time. And immediately you have a problem, because we have a horizon, we have a region of space we can see with our telescopes, and beyond that we can't see. So we're almost in principle excluded from being able to see other members of an ensemble of universes if they lie outside of our space-time. The best people have come up with theoretically is the possibility that these other universes in a multiverse scenario might somehow imprint their existence in gravitational waves into our universe. It's very speculative, very theoretical. Nobody's figured out any way to measure such gravity waves or even predict the form of those gravity waves. So for the moment, the multiverse is just a cute idea with no experimental support. Ready for the next question?
Salih Majid, who's on with us live, asks, why is it that stellar black holes are rare in the universe?
Stellar black holes are rare because massive stars are rare. So there are roughly 100 red dwarfs of mass about 2/10 the mass of the sun for every star like the sun. Equally, there are about 100 stars like the sun for every star that's 10 times more massive than the sun. And it's a star that starts its life as 10 times the mass of the sun after losing much of its mass through its lifetime, that could leave behind a 3 or 4 times the mass of the sun black hole. So the stars that will form black holes late in their short lives are dozens up to 100 or so times rarer than the sun, and so obviously there are not that many of them. The prediction is that there are roughly 10 or maybe 20 million stellar mass black holes in the Milky Way galaxy. But obviously the Milky Way galaxy has several 100 billion stars, most of which are dwarf stars. And so that's a measure of how rare they are. And the same will be true in other galaxies too. Ready for the next question?
All right, our next question is from Marcos, who's on with us live, who asks, do you think that non-traditional telescopes, such as infrared and radio, etc., will ever be cost-effective enough for the layperson or small organization to be able to afford one, and why or why not?
That's a good question. And the answer is yes. For example, remember that radio astronomy started with amateur radio astronomy. In the 1930s, Gro Reber was an engineer, an electrical engineer who sort of took early retirement. He was laid off, but he essentially took early retirement. And for a decade, he was the only radio astronomer in the world. Karl Jansky eventually became still a professional radio astronomer only because his employer allowed him to do it. So radio astronomy was definitely a domain where amateurs were right there at the birth of the subject. And amateurs continue to do radio astronomy into the present age. It's not as well known or much talked about as optical amateur astronomy, but for people who have a radio background or an electrical engineering background, it's actually not hard to do centimeter wave radio astronomy, building the dishes and the receivers and dealing with the data and the computation. It's not that challenging. So radio astronomy, right from the beginning, 1930s, through the present day and into the future, will be the domain of amateurs. Infrared is trickier, but also the technologies are improving. So infrared CCDs are now coming down in price. They're increasing in size or number of pixels. such that professional astronomers have infrared CCDs that are just as big and sensitive as their optical CCDs. And I think now, even now, amateur astronomers can get their hands on infrared CCDs. However, for that purpose, they actually have to buy slightly expensive equipment because you need cryogenic cooling. So amateurs are familiar with using cooling for their optical CCDs. Some do not need it at all, but if you want to cool them and get lower noise, you use a thermoelectric cooler. That is just a electrically powered cooler. If you want to do infrared observing, you have to take your instrument down to the temperature of liquid nitrogen, so you need cryogenic cooling. But doers that can use liquid nitrogen, remember liquid nitrogen, one bought in bulk is about the same price as milk. It's not that expensive. Doers are also available. So I know that amateur astronomers are already experimenting with infrared observing, and that probably will increase in the future as those technologies get more available. So there's really not much that amateur astronomers can do. I would say the exceptions are, of course, UV and gamma ray and X-ray very high energy observing, where you essentially have to go into space. So people can't do it from the ground. Everything else is fair game. Ready for the next question.
All right, well, this will be the last question for today's live session, and the question comes from Salim Majid, who asks, why is our galaxy disc-shaped, but planets are spheres?
So in astronomy, when you see something that's disc-shaped, whether it's a galaxy or the orbits of a solar system or the ring system around a giant planet, it's usually a reflection of angular momentum. So most astronomical situations involve angular momentum, which is to say that the gas clouds out of which objects form, like galaxies or stars or solar systems, tend to have a small amount of rotation. They're not perfectly spherical and non-rotating. And that's just because of the sort of turbulence and chaotic motions in the material out of which they form. So since a typical volume of space, which has a big nebulous gas cloud that is eventually going to form something by gravity, has some angular momentum, conservation of angular momentum says that that will be preserved. And so as the object shrinks by gravity, it'll spin faster, and it will naturally collapse into a disk-like situation. So that applies on the huge scale of a spiral galaxy and on the small scale of a solar system, or on the even smaller scale of the ring system around a giant planet. And it's kind of beautiful that the same physics is responsible for all three things. Thank you for your questions today. Great questions as always. Thanks to Vicki, Matthew, and Alexander for helping with this session, and we'll be back with you in a couple of weeks.
All right, thank you, everyone. We're signing off now, and we want to remind everyone that we now have our astrobiology course on Coursera. So if you haven't checked that out, make sure you head over and do so. We really enjoyed this, and we will see you again in 2 weeks.